Out the content that's on the test. So we're on 212, which is log function manipulation. So today, some of this is review, like the expanding and condensing of logs. You definitely did in Algebra 2, so hopefully that part seems review. So, I don't even know what I was saying. Expanding, condensing, review, and then we're going to get into manipulation, meaning like what other way could this affect our graph using transformations. So like we did it with exponential, we're going to do it with log, okay? So as a refresher, our properties of logs. There are three: the product property, the quotient property, and the power property. The product property says if I'm finding the log of a product, so if it says log of any log and what's next to it is the product, then we can expand our log by adding them. And this comes from our power properties of exponents. So if you think about if I was to multiply two bases that had exponents, what do I do to condense that down to one? What do we do with the exponents? We add. So it's the same, except it's the reverse in log, right? If we multiply, we break it down into a sum. This would be x to the fifth. No, if I was to.
But I'm saying for the logs, you would kind of.
So there's two ways to look at it. This is expanding. So we're going from a product to a sum.
Oh.
So when we break it apart, and each part gets the log. Then the next one is the quotient property, and the quotient means divide, right? So if I have a quotient or a fraction where I'm dividing, when I break it apart, it becomes subtraction. And again, it comes from the rules of exponents. So like if I had x to the fifth over x to the second, what do I do with those exponents? I would subtract to get x to the third. And then the last one is the power property, which we talked about the other day. And I said I was going to come back. Here it is. Okay. And that is if I raise something to the power, it is this, if I raise a log, to a power, then I can bring that number to the front of it. And this comes from raising a power to a power, like x to the second raised to the third. What do I do with those exponents? When I raise a power to a power, what would I do with those exponents? Multiply. We would multiply, so that becomes x to the sixth. So power becomes multiplication, division becomes subtraction, multiplication becomes addition. Then we're going to expand. So it says use the log properties to expand the expressions as much as possible. So looking at log base b of x square root z to the second power. What's one way to start it? Because there's more than one way. I can distribute the 2 to both of them, the squared power. So I can make this log base b of x squared and then the square root of z squared. And that becomes, just z. So this is log base b of x squared times z. And then I want to expand it out. So this is a product, which becomes what when I expand it? Addition. So this would be log base b of x squared plus log base b of z. And then I've got a power. What do I do with the power? Push it to the front. So this becomes 2 log base b of x plus log base b of z. So another option from the beginning, I could have bumped the power forward, just so you can see another option, okay? You could have bumped the power forward, so it would have been 2 log base b of x, square root of z, and then I could expand it to log base b of x plus the 2 would go to both, 2 log base b of the square root of z. But you cannot leave a radical when we expand. So what's the same thing as, the power that's the same as the square root? 1/2. So this becomes 2 log base b of x plus 2 log base b of z to the 1/2. And then we kick the exponent forward again. And I get 2 log base b of x plus 2 times 1/2 is just 1 log base b of z. So both get you the same answer, okay? However your brain says to start it, start it. But just be careful. Questions on that one? Start the second one. What's one option? Before you subtract, though, because the 3's on the outside, you either have to bump the 3 to the front or you have to give each one the 3. So I could either make it 3 log base 5 of 25 over y, or I could make it log base 5, 25 to the third over y to the third. So either way, but at the end, when I expand this out, they both have to have the 3. So if I continue with the top, this becomes 3 log base 5 of 25 plus 3 log base 5 of y. Minus, thank you very much, minus 3 log base 5 of y. Now, anything that ends up all numeric, you have to check to see if you can simplify it. This thing, log base 5 of 25, can become what? 2. So this becomes 3 times 2 minus 3 log base 5 of y, or 6 minus 3 log base 5 of y. Yeah.
You have to do that?
Yeah. If you went the second route where you gave them both the 3 as the exponent, then this would become log base 5 of 25 to the third minus log base 5 of y to the third. And then this could simplify 2 ways. I could either kick the 3 to the front, right? And then do log base 5 of 25 would be 2, and 3 times 2 is 6. Or I could change this to be log base 5 of 5 squared raised to the third. And then what happens to my exponents here? I'd multiply them. So that could be log base 5 of 5 to the 6th. And what happens when the base on the log is the same as the base on what's next to it? It cancels out and becomes 6. So like 7 different ways to do the same kind of question. At the end, you got to get to the 6 either way. And then this 3 bumps forward, so minus 3 log base 5 of y. So when you expand, if your expansion, it doesn't mean it's always going to simplify, but if you end up with no variables there, or next to each other, next to the log and the base, then you got to see if you can simplify it. It doesn't mean it would always be simplifiable, but you have to check it. Questions on that one? Okay, last one. So what is that square root the equivalent of in an exponent? A 1/2. So this is x to the 5th, y to the 7th, raised to the 1/2. Give me one option of where to go from here. I could bump the 1/2 to the front. What's the other one? Can I distribute the 1/2 to here? Yeah, because this is a product, right? If this was an addition statement, I couldn't, but it's a product, so you can. So one option, 1/2 log x to the 5th, y to the 7th, which then becomes 1/2 log x to the 5th plus log y to the 7th, or 1/2 log x to the 5th plus 1/2 log y to the 7th. Log base 3. All these base. Thank you. Base. I did it on purpose to stress how important it is not to forget your base on your logs when you expand. All right, now all those exponents kick forward. Multiplies. So I get 5/2 log base 3x plus 7/2 log base 3y. And again, other option from here is distribute. So it would have been log base 3x to the 5/2, y to the 7/2. Expand log base 3x to the 5/2 plus log base 3y to the 7/2. And then kick them forward. 5 halves log 3x plus 7 halves log 3y. So same answer in the end, 2 different ways to do it.
Do you want us to write it like 7
Right, questions on expanding? Okay. Now, expand. Do you guys try these? Expand and remember our LNs, right? LN is the same thing as log base what?
E.
Log base E. Okay, you do these. Just expand so far. I'm going to expand it. And the most common mistake made with expansion on logs or condensing on logs is if there are 2 things in the bottom. If there are 2 things in the bottom, they both get the minus. If there were, and it's the reverse, if I'm condensing this statement, every positive goes in the top, every negative goes in the bottom. Order does not matter. I could put this at the front, I could lead with a negative, and that still goes in the bottom. So if it's in fraction form, when you break it apart, everything in the numerator would have a plus or be positive, and everything in the denominator would be minus or negative, okay? And then vice versa. So now what is log base 9 of 81? 2. This one, the 4 kicks forward, 4 log 9a minus 3 kicks forward, 3 log 9b. And this kicks forward minus 3 log 9c.
I understand why it's a negative though.
Well, if you broke it down into parts, let's say we divided it at its fraction, right? Let's say we started there. It would have been log base 9 of this product, 81a to the 4th, minus log base 9 of this product. Now, if I break apart the product, there's a minus at the front of this product, and that minus would get distributed to both. I mean, that's just the rule of, like, a negative would get distributed no matter what. That's a rule of, like, anything.
Okay, it's because of the negative that's in front of there.
Correct.
Okay.
Yep. That negative, that minus is saying minus that product,
Okay.
which means they both get the minus.
Okay.
Does that make sense?
Yeah.
Okay. Yeah.
Oh, did you mean to put a 3 there?
Where? Oh, no, this should be a 2. Sorry, 2. Thank you. Is that all the answer? Yeah.
Would it be acceptable if you jump in like parentheses like this and you just put a negative in front of them? Like
No. Got to keep going. Yep. All right. So now I did number 5, ln of e to the 3rd minus ln of e. Ln of 8. Can either of those be simplified? What is ln of e to the 3rd? 3. So this becomes 3 minus ln of 8. Anytime you see ln of e, you got to simplify it. It gets you the exponent, okay? I did right. All right, now the next one's a little tricky because as it is, this is not a sum or a difference, right? I mean, a product or a fraction. So I cannot expand it as is. But what? I can factor out a 10. So if I were to factor out a 10, it would say log, it'll eventually hopefully catch up, x minus 5, log 10 times x minus 5 is what I have written. And then this is a product. So this can get split up, and it would be log 10 plus log x minus 5. And log 10 is what? 1 plus log x minus 5. It hates me today. Okay, now we're going the other way. Same product, quotient, and power property. All right, we're going the other direction. So now you're going to have something that starts spread out, and it's going to have multiple logs, and you're going to condense it down to 1 log. Has to get to the point of 1 log, okay? Most of the instructions, even on your AP exam, will say express the following as a expression with a single log function, okay, which means 1 log. So now we're going the other direction. Anything that has a power, I would say, is where I start. I kick back the power from the beginning, and then I do the condensing. So something like a, this 1/2 is going to go to the a. So it'd be log base 2 of a to the 1/2 plus the 3 is going to go to the b. Log base 2 of b to the 3rd. Now, usually they're the same log. If they're not the same log, we can't condense them. They're both log base 2. So the addition then becomes what? Multiplication. And a to the 1/2 becomes square root of a. Okay, second one, the power of the 2 goes, or the product, the number on the front becomes the exponent on the y. And this time it's a minus. So this is log 6x over y squared. You can put the parentheses around it. You don't need the parentheses. It's implied that they're there if it's just one fraction.
So b to the third on the outside for the first one. It's not under the square root.
It is not under the square root. Good. All right, then we go to the next one. The 2 comes to the 3, so now it's 3 squared. And then the 5 goes to the x. So this becomes log 3 squared, and it's a minus, so it goes over x to the 5th. And then we're going to go one step further, and we're going to simplify. 3 squared becomes 9 over x to the 5th. And then the last one, so the 2 becomes the exponent on the y, the 5 becomes the exponent on the x, and I get ln x minus 2 over y to the 2nd. Where's the x to the 5th go? In the top. And then you can leave it like that, okay? If it was multiple choice and you saw this distributed out, obviously it'd be different, but for the most part, you could leave it like that. If it was open-ended, you could certainly leave it like that.
Wait, if it was a reverse constant, put ln as log b.
No, you would leave it as ln. Yeah, ln is technically simpler than log base e. You only convert it to log base e to simplify it if it had an e in it. Yeah.
Why does the x to the 5th go to the top?
Because it's got a positive. So positive top, negative bottom. Yep.
For the first one, did we have to, like,
Now we're going to take the graphs and the expanding and put it together. So compare the graph of log base 10, obviously, because it says log, of x to the graph of g of x equals log 100x. So what's one transformation that I would get without having to simplify it all? How would I describe the transformation from f to g? Horizontal dilation by a factor of 1 over 100. Now, if it said expand and then describe the translation, my log of 100 times x becomes log of 100 plus log of x. Log of 100 becomes what? 2 plus log of x. Now, what's that translation? Vertical shift up 2. So if it says expand and determine the translation, that would be your answer. If it said give all of the ways to describe it, it would be both, right? If it's multiple choice, it would be obvious. It won't be like one or the other, or it will be one or the other. Yeah. A horizontal dilation would take it, and it would, this by a factor of 100, 1 over 100 is really like this, which would be the same thing as this. Because this part of your curve, like, well, this part stays pretty vertical, right? So either you're flattening it out, well, actually you're flattening it out so it does this, which makes it sharper on the top, or you're pulling it up. It's the same thing. Yeah. So, and that goes, we did it with exponential too, remember? A horizontal dilation was the same as a vertical shift, or it was a horizontal shift was the same as a vertical dilation. Now it's reversed because they're inverses of each other. Yeah.
how did you know when it said, like, add them? Or were you just doing it as
If it said to expand, you had to expand and then figure out another way to describe the same translation.
Did we, like, add them together to expand them? Or?
Well, no, we expanded because it was a product. It became addition. Yeah.
I didn't know which one you were
Okay. Always compare the graph would be what's happening on the second graph. Yeah. Okay. The example 3 says find the domain and range and describe any transformations of the graph. So let's see if we can expand them. This would all be an expansion. Then describe, well, we can do it in either order, but we're going to expand and then do the domain and range. So let's practice our expansion. Log base 3 of 9x becomes what when we expand it? Log base 3 of 9 plus log base 3 of x, and log base 3 of 9 becomes 2. So here's what it would look like in its expanded form. What would be the translation on that graph from my original log base 3 of x? This would be up 2. Yep. The base is really your parent function, but it's still just a log. So if I went off my initial log, right, this would be a log that had a horizontal, it's by a ninth, so it would have been smaller. It would have been here. The horizontal dilation has no impact on my domain or my range, right? Because it would just make it narrower or wider, but it doesn't shift my vertical axis or my vertical asymptote, which is what's going to change the domain. And the range of every log is what? All real numbers. So no matter what we do to these, it's going to stay, okay? So based on the initial, which would have been a horizontal dilation by a factor of 1/9, my domain doesn't shift from the parent function. It's 0 to positive infinity. And my range is all real numbers. Now, if I expand it and look at it, all I've done is taken it and shifted it up. Didn't change my vertical asymptote, so my domain stays the same, and range is always negative infinity, positive infinity. Go to B. What are you going to do to expand this out? You got to take out a 16. Right? I got to make it a product. So this would be 16 times 1 minus x. When I expand it now, log base 4 of 16 plus log base 4 of 1 minus x. Log base 4 of 16 is what? 2 plus log base 4 of 1 minus x. What's the 2 on the front doing? It's up 2. It's not multiplied, so don't confuse it with a stretch. This is up 2. Does that change my domain? No. Does it change my range? Log range never changes. And then on the inside, what's that? There's two things happening here, right? The negative on the x is a reflection over the y-axis, which means I'm pointing to the left, right? Does that change my domain? Yeah. Yes. And where's my vertical asymptote? X equals 1. Always set the parentheses equal to 0 to find your vertical asymptote, right? This would be at x equals 1 because it would be left 1, but then the negative flips it over the axis to now make it right 1. So find your vertical asymptote by setting it equal to 0. That's way easier. My vertical asymptote is at x equals 1. So my graph is at 1 and it's pointing to the left and it's shifted up 2. What's the domain? Negative infinity to 1. What's the range? All real numbers. Yeah.
What about the plus 2? What did that...
Shifts it up, but doesn't change my domain, right? Okay. Now, log base 2 of x to the 4th. Good. Bump it to the front. So when we expand that bumps to the front, this becomes 4 log base 2 of x. The 4 on the front is what kind of translation? Vertical dilation, factor of? Good. Does that affect my domain? No, it's still pointing to the right, so domain is 0 to positive infinity. Range is always all real numbers. So remember, in terms of logs, domain is the thing that can change. Range will always be all real numbers. So if domain can change, it's all based on your horizontal. If it shifts left to right, if it's a reflection over it. Those are the things that are going to change your domain.
Wait, so was it left to right 1?
This, well, it depends on how you pair it. Remember, you can either say this is negative. Well, if I do it as negative x plus 1 and I keep it together, then it's to the left 1 over the y-axis.
Okay.
If I separate out the negative, then it's to the right 1, literally flip the curve not over the y. Does that make sense? So we point it left instead of going over. Yeah. But if you do the, like, where's my vertical asymptote, I think that's the easiest way to figure out your horizontal shift. Because that, you set it equal to 0. That is your vertical asymptote. You don't got to worry about was it flipped or not. That's where it's at.